Okay, so welcome everyone. Today we will be presenting MICR017 methodology, integrated direct air capture and microalgae carbon removal methodology, which is currently under public consultation as part of the ICR methodology approval process. The objective of this session is to provide context on ICR's framework, introduce the methodology approval process, and then hand over the methodology developers to present the technical scope, key features, and intended applications of the methodology. Most importantly, this session is part of the public consultation process, and we welcome your questions, comments, and feedback. So before we begin, I would also like to highlight that ICR now has an event section on our website. There you can find information on upcoming webinars, workshops, and on-demand recordings from previous sessions. This is part of our effort to make methodology consultations and stakeholder engagement more accessible and transparent. But for today's session, it will be structured in 3 parts. First, the ICR will provide a brief overview of the International Carbon Registry and the methodology approval process. Second, the methodology developers will present MICR017, including its scope, key features, and applications. Finally, we will open the floor for questions and discussions, and we encourage all participants to use this opportunity to engage directly with both ICR and the methodology developers. And you can add questions at any time during the webinar. If you just go to the bottom right corner of the page, and you can add a QA question, and we will try to answer them accordingly during the QA session. But yes, today we are joined by representatives from ICR, ARCSI, and Ecovita Climate. From ICR, Guðmundur Sigbergsson, ICR's CEO and founder, will provide the introduction and overview of the methodology approval process. From ARCSI, we are joined by Dr. Senthil Chinnasamy, Director and Chief Scientific Officer. Dr. Senthil is an environmental biotechnologist with a PhD in microbiology and more than 34 years of research experience, including 24 years in industrial and applied R&D. His work focuses on microalgae-based CO2 capture, DAC algae integration, carbon mineralization, low-carbon fuel pathways, and circular carbon economy solutions. We are also joined by Marcin Nguyen, who leads business development and carbon strategy. Marcin works across carbon removal, MRV, and climate infrastructure, and previously represented Verra across the Middle East and Africa. He now supports ARCSI's partnerships and market strategy across the Middle East and APAC. From Ecovita Climate, we are joined by Aniket Kumar Shaw, co-founder and lead for Natural Climate Solutions. Aniket works across voluntary carbon markets, nature-based solutions, and carbon project development, with a focus on credible, measurable, and implementation-ready climate projects. Together, the speakers bring expertise across carbon markets, methodology development, microalgae systems, DAC algae integration, and project implementation. And now I'm going to hand over to ICR CEO, Gummi, who will take it from here.
Thank you, Björn, for this introduction. Another development team, the developers team, prepared a detailed presentation of the methodology itself. So I will try to keep my introduction brief, as brief as possible. But at ICR, methodologies go through a structured approval process. This includes methodology development, public consultation, independent validation by an approved VVP, ICR internal review, and then the final approval. The purpose of the process is to ensure that methodologies are transparent, technically robust, conservative, and aligned with international standards. A short intro about ICR for those who are unfamiliar with ICR. But ICR is both a global GSC program and a registry platform. ICR supports a wide range of climate projects and methodologies. Today, the platform includes more than 200 projects. Over 10 methodologies are approved or in the process of becoming approved. More than 25 VVPs and over 130 developers are under our network. And we also have like a growing network of marketplaces and resellers of the output of all the projects that are registered in our under our program. Our goal and mission is to support credible climate action through transparent project registration, robust accounting, and independent validation and verification. ICR supports climate innovation and the development of new methodologies where existing methodologies do not adequately cover an activity. To be approved under ICR, methodologies must align with ISO 40064-2 ICR requirements, undergo validation by an approved VVP, be subject to public consultation, which is ongoing for this methodology, and complete the ICR final review and final approval. This allows new and emerging climate solutions such as this integrated DAC and microalgae approach presented today to be assessed in a structured and transparent way. ICR builds on ISO 40064-2, which establishes the fundamentals for project-level accounting. ICR then adds carbon market-specific requirements, including eligibility criteria, safeguards, additionality, permanence, avoidance of double counting, and crediting rules. Methodologies act then as a blueprint for applying those criteria consistently. They define how projects determine baselines, establish boundaries, quantify impacts, monitor data, and demonstrate that the resulting GSG benefits are real, measurable, additional, transparent, and conservative. To support developers, ICR provides methodology requirements, template, definitions, and process documentation. This helps to ensure that methodologies are prepared in a consistent way and can be assessed efficiently by ICR, VVPs, and other stakeholders. For this methodology, this means that the methodology should clearly describe the project activities, applicability conditions, baseline, and project scenarios, additionality approach, quantification framework, leakage, permanence, and monitoring requirements. So, what is a methodology? In simple terms, a methodology is a set of criteria and procedures for measuring, calculating, monitoring, and reporting on greenhouse gas emission reductions or removal. It serves as a recipe for project development and carbon accounting. For this methodology, the focus is on integrated carbon removal pathway, capturing CO2 from the atmosphere through direct air capture, transferring that CO2 to microalgae cultivation systems, and storing carbon in durable end products. A robust methodology ensures that these outcomes are quantifiable, verifiable, conservative, and suitable for independent validation and verification, and demonstrate conformance to the validation and or verification criteria. This slide summarizes the key components that are required under the ICR methodology requirements. A methodology must address the scope, normative references, definitions, principles, general requirements, and the core methodology components. These include other methodologies or sources, summary description, definitions, applicability conditions, boundary, baseline scenario, additionality, quantification, and monitoring. These are the areas that are assessed during the methodology approval process and where stakeholder feedback is particularly valuable. The ICR methodology description template provides the structure for the methodology submission. It ensures that important elements are not overlooked, including other methodology considered, applicability, boundary, baseline, additionality, quantification, leakage, permanence, risks, and monitoring. As of now, we are still relying on the traditional work template, but we are actively working on how to digitize the methodology descriptions or the application or the criteria. So this for the process itself. This slide intends to summarize or illustrate the methodology process. So the process starts with the methodology development and where relevant, a concept note and ICR review. The methodology is then developed further, published for public consultation, validated by a VVP, reviewed by ICR, and then submitted for approval. This process is iterative. Comments from stakeholders, ICR, and the VVP may result in revision before the methodology is finalized. The public consultation is therefore not just a formality, it's an important opportunity to improve the methodology before it enters into validation and approval. For the ICR017, the concept note was submitted to ICR in July last year, and we reviewed that and gave some feedback on the further development of the methodology. The draft methodology was then developed and is now undergoing public consultation during April and May. Following the public consultation, ICR will consolidate all the comments that are received and share them with the methodology developers. The developers will then need to respond to the comments and revise the methodology as appropriate before it proceeds to validation and further review. And of course, the VVP needs to consider any public comments that are received during the public consultation. The public consultation for the ICR017 integrated direct air capture and microalgae carbon removal methodology is currently open. I will close on the 27th of May. We encourage all participants and anyone later viewing this webinar recording to review the methodology and submit comments through the consultation page. You can scan this QR code to access the consultation page. Stakeholder feedback is an essential part of ensuring that the methodology is robust, transparent, practical to apply, and aligned with environmental integrity. With that, I would now like to invite the methodology developers to present the ICR017 in more details. Thank you. Thank you all. So I think Marcin,
yes, that's correct. I can start sharing my screen, right?
Yes, I think I start sharing mine, and I will mute myself.
Okay, just let me know. You should be able to see the entire screen by now, right?
Yes.
Yes.
Awesome. All right, excellent. Well, then good afternoon, good morning, everyone, and thank you again, ICR, for hosting this webinar. I'm Marcin from ARCSI, and today's methodology was developed jointly by ARCSI Holding and Ecovita Climate. So our purpose today is essentially walk you through how this methodology works and to invite you for feedback as part of the public consultation process. And of course, we welcome your questions at the end of the presentation as well, right? As mentioned, the methodology MICR017 is the integrated direct air capture and microalgae carbon removal methodology. The methodology is currently under public consultation with ICR, and it sits within the carbon capture and storage sector. It is structured as a hybrid of carbon removal, combining engineered capture with biological fixation. So in plain terms, the CO2 is captured directly from ambient air used to grow microalgae, and then converted into durable products, things like concrete, biochar, engineered stone, and or soil amendments. Today, we will move through 6 areas. We'll start with the context, of course, mentioning why this methodology exists and what problems it is currently solving. Then we'll give an overview of the methodology itself, what it applies to, what is in the scope, and what sits outside it. Thirdly, we will walk through the core of carbon accounting logic. So that would cover baseline, additionality, and quantification. This is pretty much the heart of the methodology, so we might spend a bit more time there. After that, we will cover the technology pathways. That covers the DAC systems, algae cultivation, and durable product storage options. And then fifth, we will address the leakage, permanence monitoring, and risk management. And finally, we'll open the floor to your comments, questions, and any technical feedback that you would like to share with us. The goal is pretty straightforward for this call. We want to make sure that you leave with a clear understanding of how this methodology works and what type of advantages it will bring to the innovation within the carbon world. So I will start here just by highlighting why the methodology is needed. The starting point is quite straightforward. Emission reductions remain essential, right? But they are no longer enough on their own. So most credible net zero pathways now require active removal of CO2 already in the atmosphere, not just reducing what we add to it. So this methodology addresses one specific removal pathway, which is combining direct air capture, which separates CO2 from ambient air, with microalgae cultivation, where that CO2 is biologically fixed into biomass. But capture alone does not earn a credit, right? So the final and most critical step is durable storage. And that's where the biomass must be converted into products that can hold the carbon for at least 100+ years, right? And that's why the methodology connects three elements. So one is the atmospheric capture, two is the biological fixation, and three, lastly, is the durable storage. And that turns into a full chain of carbon removal framework, so to say, which is, of course, the goal is to make it as measurable, conservative, and verifiable as possible by the design. That being said, I will let Dr. Senthil to take over from here, and again elaborate a little bit more why this methodology matters in the current part. Dr. Senthil, I'll give it up to you to take over the mic.
Yeah. The next slide, please, Marcin.
This one, right?
No. Previous. Yes.
There you go.
Thank you, Marcin. And good day to you all. My name is Senthil Chinnaswamy. I am the Director and Chief Scientific Officer of Oxy Group. So before discussing the technical aspects of the methodology, it is important to understand why this methodology was developed and what problem it is trying to address. Today, one of the biggest challenges in carbon removal is not simply capturing carbon dioxide, but demonstrating that the removal is scientifically credible, measurable, verifiable, durable, and conservatively accounted for. So this methodology is built on 5 principles that together define what a credible carbon removal methodology should look like. The first one is credible CDR. The methodology applies conservative accounting principles with full traceability across the carbon pathway. The intention is to avoid inflated claims and ensure that only scientifically defensible net removals are credited. The second one is atmosphere capture. So here, the methodology considers only carbon dioxide captured directly from ambient air through direct air capture systems that qualifies under this methodology. Point source emissions and flue gas CO2 are excluded from the scope. The third one is interesting, and this is biological fixation. So basically, it is an integrated technology which integrates engineered carbon capture with biological fixation, where we cultivate algae in the saline water and wastewater streams, and thus carbon supplied through the engineered carbon systems gets captured by the algal systems and stored in their biomass. The fourth one is durable storage. Once the biomass is produced and the carbon is stored in the algal biomass, now the methodology focuses on long-term storage pathways where the captured carbon can remain retained in durable products such as algae-derived concrete, mineralized materials, engineered stone, stabilized biochar systems, and certain stabilized long-life soil additives. And finally, net crediting. Credits are issued only after detecting life cycle emissions, leakage emissions, operational energy use, transport emissions, and potential re-emissions. So the methodology, therefore, focuses on net atmospheric carbon removal rather than gross capture alone. Next one. So based on these 5 principles, we will now briefly show a few illustrative deployment concepts and pilot systems relevant to the methodology framework. Here you can see DAX system integrated with open raceway pond microalgae carbon removal system. The first one that captures CO2 from ambient air through modular DAC units. They use scalable solid sorbent or membrane-based systems. The extracted CO2 is stored in the buffer tanks, and the stored CO2 is being used for cultivating algae in the open ponds, open raceway ponds or open static ponds, where the saline water and treated sewage water or wastewater are being used as a cultivation medium, and the CO2 gets dissolved in this medium that is being absorbed by algae, and the algae produces the biomass. This biomass is harvested and it is dewatered and dried, and this dried biomass is further converted into durable storage products like multiple durable products like algae-derived concrete, biochar, and soil amendments. Next slide, please. So these are all not only concepts which have been already demonstrated under real-life conditions in arid ecosystem prevailing in the GCC region. So these are all open raceway ponds in a pilot facility where we tested the carbon capture potential of microalgae using saline water and wastewater sources. So this clearly establishes the proof of concept that algal systems can be used for capturing carbon from ambient air as well as point source emissions. And this study provided the potential of algae-based CO2 capture per hectare and the biomass productivity potential of algal biomass cultivated in the open ponds. So this clearly indicates this kind of open pond systems can be integrated with DAX system. Next one. So this is the, another concept depicted where the photobioreactors instead of open ponds are integrated with the DAX systems. You can see here the same thing. The CO2 is extracted from the ambient air and that is being stored in the buffer tank, and it is supplied to the algal cultures being cultivated in closed photobioreactors or hybrid reactors kind of thing. And the entire power like supply is from renewable sources to reduce the carbon intensity. And once the algal biomass is harvested and converted into the products, and that can be verified. And this is where it is very important that a very important part of this concept depicted here is the MRV, monitoring, reporting, and verification. This system should track CO2 capture, CO2 flow, biomass productivity, energy use, and final product carbon storage. This helps create a traceable carbon pathway from atmosphere to durable products. Next one. So this is a system demonstrated again in the GCC region, and it shows different types of photobioreactors, closed photobioreactors, used for capturing carbon from ambient air, and this clearly establishes the proof that we can integrate these PBR systems with that system for capturing carbon. Next one. So once you capture carbon and produce the biomass, how you are going to store that carbon for claiming permanence. So here it shows durable carbon storage pathways using algal biomass. So the algal biomass harvested from open ponds or photobioreactors can be used to replace 10 to 15% of cement in the concrete mixture, and you can produce various products like hollow bricks, solid bricks, artificial reef blocks, paving tiles, and cable tiles. So we did a proof of concept for that to mix the algal biomass produced in the open ponds at photobioreactors with the concrete mix, and we tested its quality. And that clearly indicates that we can take this biomass to prove the carbon storage potential. So now I would like to hand over to Aniket from EcoWeather Climate, who will take you through the methodology framework in more detail. Thank you.
Yeah. Good morning or good afternoon to all the participants. I'm Aniket, and I will now be discussing each component of the methodology. So the current slide presents a summarized version of the draft methodology. So the methodology is to be registered with International Carbon Registry, ICR, and has been classified as a hybrid project type, and falls under the sectoral scope 16, that is carbon capture and storage. Now, at its core, the methodology quantifies CO2 removal achieved by integrating direct air capture with microalgae cultivation. A cradle to grave life cycle assessment approach has been applied so that every operational input material consumed and that emission stream is accounted for. And the captured CO2 is then locked into durable products that provide long-term storage, thereby ensuring that what is claimed as removal is A, conservative, B, verifiable, and C, credible at every step. Now, the methodology has not been developed in isolation. It builds on 4 well-established international foundations to ensure alignment with the broader carbon accounting ecosystem, and provides the project developers and validation verification bodies a familiar framework for project development and project review. Can we move to the next slide, please? Thank you. So talking about the eligibility criteria, eligible projects under this methodology must operate a direct air capture system using either solid sorbent, liquid solvent, or membrane technology. And the system must demonstrate a technology readiness level of 6 or higher. The captured CO2 must then be routed to a microalgae cultivation system where an open raceway pond, a closed photobioreactor, a hybrid configuration, or a container-based portable system can be used. The resulting biomass must be processed into durable end-use product with documented service life of at least 100 years, such as Dr. Senthil mentioned, concrete, biochar, soil amendments, or engineered stone. Full traceability is mandatory across the entire pathway from the moment carbon dioxide leaves the atmosphere to the moment carbon is locked into the final product. Now, the methodology is scale agnostic and accommodates pilot installations below 1,000 ton per year, then intermediate installation of 1,000 to 5,000 tons, and commercial installation above 5,000 tons annually. The methodology allows project activities to be implemented in different configuration, which includes your centralized industrial hub installations, then modular distributed systems, community integrated formats, building integrated systems, other commercial establishments such as any food and beverage establishment, hospitality venues, and also the coastal installations. Now, there's a point that I would like to highlight here, that the methodology does not restrict any project developer to any of the single configurations, and multiple configurations can be integrated within a single project activity. Further, talking on the eligibility criteria, the project activities may accommodate integration of different energy sources to support DAC and algae cultivation system operations, including renewable energy sources, grid electricity, biofuels, low carbon fuels sources, bioenergy applications, and industrial waste heat recovery systems. The methodology also applies to retrofit applications involving integration of DAC systems into existing facilities, including algae cultivation facilities, wastewater treatment operations, industrial facilities, commercial buildings, and other existing infrastructure configurations. Now, as per the draft methodology, the project design should not result in deforestation, conversion of natural wetland, conversion of agricultural lands that are currently under cultivation, or any loss of critical or important habitats or ecosystem. And it is mandatory that all project needs to undergo an environmental impact assessment or any equivalent environmental screening. Now, as far as the methodology is concerned, the usage of groundwater is prohibited unless the project developer demonstrates that use is legally permitted and environmentally sustainable with adequate aquifer recharge and does not compensate with essential agricultural or municipal water needs. Now, on the exclusion side, like cases where the methodology does not apply, enhanced oil recovery and any other fossil fuel extraction using captured CO2 are not eligible. Flue gas and point source CO2 streams are also excluded. Biofuels, synfuels, and any other short-lived energy carriers where the carbon dioxide be reoxidized back into the atmosphere are also excluded. As I've already mentioned, that the projects that cannot demonstrate end-to-end traceability and projects involving uncontrolled land use change, including deforestation or disturbance of wetlands and peatlands, are likewise outside the scope. Next slide, please. Thank you. So the methodology follows every ton of carbon across 4 sequential stages, from atmospheric capture through final product utilization and end use. Stage 1 is atmospheric capture, covering the DAC equipment itself, the separation process, intermediate buffer storage, and any compression required to ready the CO2 for transfer. Now, stage 2 is about the biological fixation, which captures everything related to algae cultivation, be it the ponds or photobioreactors, the water and nutrient supply, and the infrastructure that delivers carbon dioxide into the culture. Now, stage 3 is downstream processing, covering dewatering, drying, conversion of biomass into end-use products, and packaging. And finally, stage 4 is product utilization, which extends to transportation, deployment, and the in-service phase, during which the carbon remains locked away. Now, there are 3 further design choices which are worth highlighting. One definitely is the fact that the methodology accounts for three greenhouse gases, particularly carbon dioxide, methane, and nitrous oxide. The life cycle assessment is to be conducted in accordance with ISO 14064. And finally, two emission sources have been treated as de minimis and therefore excluded. One is the facility construction and the other is equipment manufacturing, on the basis that these are one-time upstream emissions whose annual contribution falls below the materiality threshold over the project lifetime. Next slide, please. Thank you. So this slide presents the framework used to establish both the baseline scenario and additionality. For baseline, after a systematic barrier analysis of alternative pathways, which could include algae cultivation without DAC, or DAC without non-algae end uses, then alternative carbon removal technologies and others, the continuation of the pre-project condition has been identified as the most plausible outcome in the absence of carbon credit revenues, as far as the draft MET is concerned. Now, because no deliberate atmospheric carbon dioxide removal would otherwise occur, the baseline emission are also set as 0, which means every ton the project removes is genuinely additional to the business as usual case. Now, if you see the three boxes below, it presents the additionality test as far as this methodology is concerned. Now, all the three components must be satisfied. First, we'll talk about the regulatory surplus, which requires evidence that no binding law or jurisdictional mandate compel the project developer to implement this project. And here I may also add that voluntary policy initiatives do not count as a mandate. Then we come to the second stage, that is the investment analysis, which requires the project proponent to demonstrate that without carbon credit revenue, the project's net present value is negative, or that its internal rate of return falls below the hurdle rate that the project proponent has set out and has justified in their PDD and to the verifiers validation in the verification body. Now, in short, just to understand this concept, it is all about the fact that carbon revenue must be financially necessary and not just be treated as merely beneficial. The third and the final crucial step would be the common practice test, which requires the project proponent to show that the integrated DAC algae system have a market penetration rate below 10% in the relevant geography, or they can also opt for the first of its kind stature, as has also been mentioned in the draft methodology. Now, when we take all these steps together, these three filters ensure that the credits are issued only to those projects that genuinely would not have happened otherwise. So can we move to the next slide, please? Thank you. Now, I'll be discussing the quantification logic in conceptual terms. And we start with the gross atmospheric carbon dioxide captured by the DAC system. This is to be measured continuously at the DAC outlet using calibrated NDIR analyzers and flow meters, so that the foundation of calculation is direct and instrument-based rather than estimations. From this gross atmospheric carbon dioxide capture, three categories are subtracted, as you can see. One is your life cycle emission, re-emission, and leakage. And we'll be talking about all three one by one. So the life cycle emissions are organized into 4 sub-components. And this is where the cradle to grave LCA or life cycle assessment framework actually comes into place. So the first component that we talk about is the operational emissions. So this captures the energy footprint of running the integrated system and is typically the dominant contributor. On the DAC side, it includes electricity for fan, blower, vacuum, pumps, and compressor, together with thermal energy for sorbent or solvent regeneration where applicable. On the algae side, it covers the energy used by the cultivation system itself, such as paddle wheels in raceway ponds, circulation pumps, and temperature control in photobioreactors, lighting where required, followed by harvesting energy used by flocculators, centrifuges, and filters, and finally, the processing energy used in dewatering, drying, cell disruption, and conversion of biomass into the final product. Now, fugitive CO2 losses at seals, joint, and leak points in the direct air system are also accounted in the methodology, with quarterly leak detection and repair protocols required for any system seeking de minimis treatment. Now, coming to the second component, which is the intermediate buffer storage emission. Now, this becomes relevant only when the DAC system operates around the clock, but the cultivation system operates on a diurnal cycle, meaning the CO2 captured at night must be compressed and held in buffer tanks until the next day, and you intend to resume during daylight. So the compression energy required for that interim storage is to be quantified explicitly, and that's what we have also tried incorporating in the draft methodology, where DAC and the cultivation cycle are synchronized. This component can be set as 0 with proper justification for the VVV and the registry body. Now, the third component of the LCA emission is the material consumption energy. This captures the embedded carbon of every consumable that flows into the system of the year, be it your sorbent material for solid sorbent DAC, solvent makeup for the liquid solvent, membrane modules for membrane DAC, macronutrients such as nitrogen, phosphorus, potassium for the algae cultivation, micronutrients, and auxiliary chemicals such as flocculants and pH adjusters. Now, each material is multiplied by an emission factor sourced first from supplier-specific LCA data, then from peer-reviewed studies, then from generic LCA database, and only finally from conservative default. So this is the hierarchy that has been maintained in the draft methodology currently. Now, talking about the last component of the life cycle emission is the transportation emission, which are split into 3 legs to ensure nothing is missed. One is your inbound delivery of consumable to the facility, internal movement of harvested biomass from cultivation to the processing plant, and outbound distribution of finished bioproducts to market. Now, each leg is quantified using actual distance, payload, vehicle type, and either fuel or electricity consumption. Coming back to the overall equation, the second primary component was the re-emission from products at the end of life, which accounts for the share of carbon that does not remain permanently stored over 100 years service life horizon. And these are the losses through chemical degradation, environmental weathering, and some end-of-life disposal or recycling. Now, this component is governed by the service life storage fraction parameter, with the unstored factor returned to the calculation as a debit. And finally, we have the leakage assessment, which captures indirect emissions such as methane from pond bottoms, nitrous oxide from nutrient cycling, market displacement effects, and respiratory CO2 release during algal metabolism. Now, throughout the calculation, the spirit of conservativeness has been enforced. The methodology talks about the data hierarchy, which I also mentioned initially, where direct field measurement under tier 1 is the first preference. If that is not feasible, then the methodology fallbacks to site-specific literature under tier 2, then to generic LCA databases under tier 3, and finally to IPCC conservative defaults under tier 4. Now, this sequencing is imperative as it helps us ensuring that whatever uncertainty exists, the bias is always towards underestimating removal benefits rather than overestimating or overstating it. So can we move to the next slide, please? Thank you. Now, in this slide, we will discuss the 3 engineered separation routes that qualify as eligible DAC technologies under the methodology. All 3 must demonstrate technology readiness level 6 or higher, as I've already mentioned. And they should ensure that the installation deployed under this framework has moved beyond the laboratory prototype into the operational demonstration domain. So the first route is solid sorbent DAC. Here, packed beds of amine impregnated sorbents or metal organic frameworks absorb CO2 from ambient air, and the sorbent is regenerated by applying heat or vacuum to release a concentrated CO2 stream. The sorbent itself is replaceable. That must be tracked in the inventory during the project rating cycle. The second route is liquid solvent DAC. In this approach, an absorption column using potassium hydroxide or proprietary amine blends capture the CO2, which is then released through a thermal regeneration step in a reboiler. Energy requirements includes electricity for blowers, pumps, and compression, together with significant thermal energy for regeneration. Solvent makeup and process losses are also required to be accounted for as far as the current draft methodology is concerned. And the third route is the membrane DAC. So selective gas permeable membranes separate CO2 from air using differential permeability and pressure gradients. The advantage here is that no thermal regeneration is required. The system pretty much runs on electricity for fan and compression alone, but membrane module themselves are periodic replacement items that needs to be monitored during the course of the project creating period. Now, by recognizing all the 3 pathways rather than locking the methodology to a single technology, the methodology developers have intended to keep the framework as adaptable as possible as the DAC sector continues to evolve, and there can be other integrated systems as well, which can be included in future. For instance, we have cryogenic processes as well. So that's why we have tried keeping it as broad as possible. Next slide, please. Yeah. So this slide shows the cultivation configuration that the methodology recognizes for the biological fixation stage. Once captured CO2 has been delivered to the cultivation system, this is where carbon is biologically fixed into algal biomass, and the choice of system has direct implication for energy use, water management, and biomass productivity. Now, one non-negotiable design constraint applies across all the six configurations that have been prescribed in the draft methodology, and it is highlighted at the foot of the slide as well. Every system must incorporate measures to prevent the escape of non-native algal strains into surrounding ecosystems. This biocontainment requirement may be met through closed system design, strain-specific harvesting protocols, or documented contingency procedures, but it is mandatory regardless of which configuration is chosen. Next slide, please. Yeah. So this slide presents the 4 durable end product pathways that the methodology recognizes for long-term carbon storage. Only those products with documented service life of at least 100 years qualify as far as this methodology applicability is concerned. The first pathway is algae-derived concrete. The second is engineered stone, where algae-derived carbon is embedded into stone composites used for construction or interior applications. Then the third pathway is biochar. Fourth is soil amendments, where mean residence time is greater than 100 years and is supported by peer-reviewed decay models or field studies. A critical concept in this methodology, as I've also mentioned earlier, is the service life storage fraction. Now, this parameter quantifies the share of fixed carbon that remains permanently stored across the product's life. It is determined through peer review life cycle assessment, accelerated aging tests, or IPCC default, where a range exists. The methodology encourages the project developer to use the lower confidence bound, and if you have a proper field-based survey to justify your choices, then of course you can go with the higher choices. Next slide, please. Now, quickly talking about the leakage, the methodology identifies 4 distinct pathways for leakage assessment, all of which are quantified and deducted before net removals are calculated. The methodology does permit de minimis treatment only with documented justification. The first pathway is methane emission released through anaerobic decomposition in pond bottoms or wet biomass streams. Given methane's high global warming potential, this is a material risk and can be managed operationally through rapid harvest, shallow pond design, and dissolved oxygen control. The second pathway is N2O released from nitrogen cycling in the nutrient media. Mitigation can be achieved through optimized nutrient dosing and aerobic conditions. The third pathway is market leakage, the possibility that algae-derived products displace conventional products and that the emission of those conventional products are simply shifted elsewhere. So the methodology takes the conservative position of assuming this to be zero unless the project proponent can demonstrate significant displacement of high carbon intensity alternatives. And the fourth pathway is respiratory CO2 released by algal metabolism during dark cycles, which is tracked through mass balance between gross fixation and net biomass retained. Next slide, please. Yeah. So the monitoring framework of the methodology is built on 3 pillars covering the entire carbon journey from atmosphere capture to final product. The first pillar is the DAC system. Hourly CO2 capture rates are to be monitored continuously. Inlet and outlet CO2 concentrations can be tracked using NDIR analyzer. Airflow is to be monitored with density correction applied. Electrical and thermal energy consumption is to be logged, and fugitive emissions are to be detected through leak detection and repair protocols. Then the second pillar is algae cultivation monitoring, where biomass yield and dry weight are to be tracked. Carbon fixation efficiency is to be measured. Water, nutrient, and dissolved oxygen levels are required to be monitored. Energy consumption of the cultivation system is to be logged, and biocontainment compliance is to be verified. Third pillar becomes the product verification, covering independent laboratory testing of carbon content of the finished products, storage fraction assessment against latest evidences, quality and durability test, chain of custody from cultivation to market, and periodic permanence reviews. Now, the QA/QC Foundation panels summarizes the discipline that holds this monitoring system together. Equipments are required to be calibrated annually with CO2 analyzer checked every 6 months. Daily automated validation runs in the background. A minimum data completeness of 95% is required, and all measurements are to be traced to ISO, ASTM, or World Meteorological Organization reference standards. Where data falls below the completeness threshold, the methodology requires conservative treatment. Next slide. So a minimum of 10% of the issued credit is contributed to the ICR adjustment account under this methodology. This is the floor, and the final percentage depends on the project permanence risk score. So there have been 6 standardized risk categories that have been identified: natural hazards like flood, fire, extreme weather, then political and regulatory changes that could mandate disposal or restrict product uses, then project abandonment risk, addressing the financial and organizational viability of long-term stewardship, then legal uncertainties around land tenure and contractual enforceability, then it can be technical performance and equipment failure risk, and finally internal organizational capacity, the institutional ability to maintain stewardship over a multi-decade horizon. Now, each category is assigned a numerical risk score, and the sum determines the project's buffer contribution. Where a reversal event occurs, the carbon previously credited as stored is found to have been released. The buffer account is drawn down to compensate. So this pretty much preserves the integrity of the issued credits without retroactively invalidating them. Next slide, please. So I think ICR team has already spoken about the feedback, so I'm going to skip this. And can we move to the next slide? Thank you, everyone. And we really hope to hear from you on the methodology, and we would be happy to hear your feedbacks. Thank you once again.
Thank you so much, Ankit, Senthil, and Marcin, for your presentation. It was really extensive, and we're a little bit behind schedule here. It was really extensive presentation. So we now are transitioning into the Q&A session. I'm conscious of time, that we have only 3 minutes left for the webinar, but I think we can manage to extend it a little bit into the next hour. So in the webinar or in the meeting, you would see the bottom right corner, like 9 dots. You can click there, look for Q&A, and there you can post your questions. And we have already received your questions as of now. So I'll just dig into the first ones. So some of them may have been already responded to. So maybe there are 2 that I can start by combining. So first, and you a little bit addressed this during your presentation, but how does the methodology address permanence and long-term carbon storage requirements? And then maybe also, what is algae-derived concrete? And maybe there's one question also that just popped up. Do we need any specific type of algae under consideration? So I'll give the floor to you. You can take those 3 questions.
Okay, so I'll go with the first one. How does the methodology address permanence and long-term carbon storage requirement? So as we have extensively discussed, that the methodology introduces the service life storage fraction, and the idea behind the service life storage fraction is that it was developed to translate a difficult question as to how much of the carbon fixed today will still be locked away for a century from the project start date. and it is expressed as, in the draft methodology, it is expressed as the fraction of incorporated CO2 that remains permanently sequestered through the product's defined service life after accounting for the 4 released mechanisms. Now, the methodology specifies 4-tier evidence hierarchy. Under tier 1, project proponents are expected to review peer-reviewed LCA studies or industrial standard databases, preferably supported by multi-year observation data or by conservative extrapolations from shorter-term data validated through accelerated aging tests. Tier 2 permits IPCC or recognized default values that can be applied conservatively at the lower bound and adjusted downwards by 10%. Tier 3 allows site-specific empirical testing with accelerated aging factors validated against field data. And only when none of the first 3 tiers can be applied, that's when the project proponent can fall back to tier 4, which is a conservative default of 0.5, which is then further carried for additional uncertainty deduction in the net removal calculation. Now, the methodology's applicability criteria is very specific about the fact that any end-use product needs to demonstrate a permanence of 100+ years, and the exclusivity criteria pretty much excludes the kind of end-use products that may have a shelf life shorter than 100 years, and that's why that's how pretty much the methodology takes care of the permanence issue. I hope that answers the question.
Thank you.
Okay, so then there's another question on...
There was the question about what is algae-derived concrete that relates to permanence, and then do we need any specific type of algae under consideration?
Okay, yeah. So we really don't need any, I mean, the methodology does not prescribe a specific algae for consideration at this stage. So the project developers are pretty they have the flexibility of using the species that they want to, unless it, it has some restrictions as far as the government mandates and policies are in place. So that is the aspect that they need to bring in and demonstrate in their EIA reports that this is native or this is accepted as far as the government policies or the mandates are concerned and not considered as non-native. So yeah, that would be the only criteria that the project developers needs to keep in mind. Then which is the next question?
The next question is for algae-based carbon sequestration projects in arid regions, what are the key cost drivers and cost-saving opportunities compared with other carbon sequestration approaches? A little bit broad question here.
Yeah, actually, this is a very broad and general question. Basically, if you, and if I'm speaking strictly based on the draft methodology, if you look at the methodology, then the cost intensive, if you ask me, would primarily be your DAC system and the operational unit associated with it. So that is pretty much your dominant factor as far as the methodology is concerned, and that would pretty much also drive your financial model. Now, cost saving opportunities, of course, there are many, but since we are talking about this methodology particularly, I think this wouldn't be a platform where I'll be able to discuss it in more details. So probably you can drop this as a question in the feedback that you'd be writing for the methodology, and we can answer it in more details. Thank you.
Thank you for that. Yeah. Iterating that, yes, please participate in the public consultation and submit your comments through the dedicated forum for the public consultation. So there are more questions coming in. Maybe we'll give it maybe 5 to 6 more minutes. But there's a question here. Can you elaborate on what technology readiness level means?
Technology. So the technology readiness level, they are basically 9-point measurement systems which are used to assess the maturity of a technology throughout its development.
Yeah, and you require that the technology needs to have reached level 6
or more.
Right?
Yeah.
All right. Then there's one more question here. How to avoid negative LCA in on such system, especially emissions associated with transporting algae biomass from the facility to the treatment product conversion facility, then to the product buyers.
Okay, so I think by avoiding negative LCA means how we can further reduce the emission during the LCA emission calculation, particularly if I'm, if I've understood this correctly. So as per the applicability criteria goes, the project developer also gets the flexibility of using renewable source of energy, which would definitely have a lower carbon footprinting as compared to using grid electricity. And that can definitely be one of the ways through which you can reduce your LCA emission during the entire quantification process. So I hope that answers the question.
Thank you for that. I have also 2 questions myself. So as a point of comparison to other DAC methodologies, such as, for example, CarbFix and the reference diametric methodology, who seem to apply a more modular structure, separating the key components of the removal chain, such as the capture component, transport, and then storage, monitoring. Did you consider to apply this modular approach, like it seems to be controlling this space?
Yeah. Yes, we did, look into the architecture, this modular architecture, which has been used by Isometric and CarbFix, and it was definitely taken into consideration. But the decision to deliver this methodology as a single integrated methodology rather than as a set of separate modules cater to 3 reasons, which I would just like to go point by point. One, or the first one, would be the fact that the integration between DAC and algae cultivation is technically inseparable in a way that DAC plus geological storage is not, which pretty much what Isometric or the CarbFix protocols focus on. The carbon dioxide transfer pathway, the buffer storage interface, and the carbon dioxide utilization efficiency are jointly determined by both the DAC system design and the cultivation system design, as far as our draft methodology is concerned. And hence we feel that accounting them in isolation would create the risk of double counting, or can also lead to the issue of boundary gaps. So that is point 1. Point 2 would be the fact that the methodology is a first of its kind, and a single integrated framework would provide a clearer reference for project developers as compared to browsing through multiple modules and cross-referencing each modules during quantification and the monitoring and other management protocols. And third would be the logic that if you look at the methodology and the way it has been structured, it it actually is divided in a lot of modules. So it talks about different life cycle stages, the 4 life cycle stages that I have also spoken about when I was presenting, and then the 3 operational domains of the monitoring section. So in a way, it is already divided in different subsections or module, as you want to call it. But yes, of course, we haven't really developed different modules for it because we wanted to have a clear consolidated methodology which can be easily implemented and deciphered by every project developer.
Thank you for this comprehensive answer to the modular approach. Then I have a clue what the answer is, but like I want to address it here. Like how, for example, the CarbFix and the Climeworks methodologies developed. Like there can be different participants in the overall project. So in this methodology, it seems that it applies it assumes that it's only one proponent that is during the full life cycle of that project activities. So, but do we envision or allow for more than one participant in the project, for example, for the DAC part, for the transfer, for the biomass cultivation part, and then the storage part?
Okay, so if I've understood the question correctly, you are asking whether more than one project entities can be a part of a project,
Yes.
Or it has to be like
more than one entity are involved in the project activities, or is it just one component?
Yes, okay, I got it. So currently, the methodology has been drafted with the assumption that there will be a single project proponent who would be responsible for the entire integrated system, be it the DAC system or the microalgae cultivation, and then further, sending it for end-use product formation. Now, this is reflected in 3 places. One is definitely the boundary definition, which encompasses all facilities under the operational control of the project proponent. Then the monitoring section, which also talks about designating single coordination team responsible for all data collection across the 3 operational domains, and the permanence buffer mechanism. But having said that, the methodology does not really prohibit multiple entity participation. Now, the applicability criteria explicitly requires the chain of custody documentation linking captured carbon dioxide to harvested biomass to final end-use product. And this kind of traceability framework is in fact best suited for multi-party value chains. So where multiple entities participate, they would probably have to be brought under a single project proponent, for example, maybe through a joint venture, consortium, or lead developer stature, with specifying what would be the responsibilities, data ownership, liabilities, etc. So yeah.
Okay, thank you. I think we covered most of the all of the questions that have been submitted through the Q&A. But like one maybe final question from our end is that like comparing like other alternatives, like the stack systems, they seem to be really expensive in implementation and operation. Like the credits, the output, they are quite expensive. So not in any details, but like high level, is this DAC approach more cost beneficial compared to the alternatives, or is it just in a comparable range?
Yeah, I think if you ask me, definitely as engineered GHG methodology, there are different other methodologies as well, which one can opt for. As far as the DAX system is concerned, and this is particularly the stance that the methodology development team takes, that it cannot really be replaced by any other GHG engineered methodology. They have their own importance, and so does the DAX system. Now, it is true that this project activity can sometimes be it can be burden on the project developer as far as the cost is concerned. But having said that, the returns that one can expect from such projects, and we have seen the overall trend of the CDR projects and the kind of value that the market is willing to give as far as per credit value is concerned, that are pretty much taking into consideration the fact that these projects are expensive in itself and requires that kind of funding or that kind of credit prices, so that the project developer can actually make these projects financially viable. So I hope that answers your question. Of course, I've tried keeping it on a very higher level, but pretty much that sums up our stance on as far as this methodology is concerned.
Okay, thank you for the answer. So I think we have covered all elements that we were intended to cover during this webinar on the introduction to the ICR017 integrated direct air capture and microalgae carbon removal methodology. So with that, I want to thank everyone that joined this webinar and remind that please submit your comments through the public consultation page. And if you have any questions, you can submit them as well to the developers and or us at ICR. So Ankit, Santil, and Marcin, thank you for your contribution. So with that, I conclude this webinar. Thank you.
Excellent.
Thank you
Thank you very
everyone.
much.